In this part, I will cover the magnetization curve and the equations describing the performance of DC machines. A DC machine has two distinct circuits, a field circuit and an armature circuit. The magnetomotive forces produced by these two circuits are at quadrature. It means that perpendicular. The field MMF is along the direct axis D, and the armature MMF is along the quadratic axis Q. Ideally, it can be assumed that the armature MMF has no effect on the field flux on the D axis, because the armature MMF acts along the Q axis. So the component of the field flux on the quadrature axis is 0, and the component of the armature flux on the direct axis is also 0. This may not be the case for practical DC machines, and there will be interaction between the two fields that is called armature reaction. However, we will just consider only the ideal case in which the armature reaction is negligible. Now let us recall the magnetization curve, or what is called the BH curve of the magnetic circuit that we have studied in chapter 1. The magnetic flux and MMF relation of a DC machine is also a nonlinear function. Hence, when we vary the field current, the flux will vary according to the iron core magnetization curve. Since the back EMF is also a function of the magnetic flux, so for a given speed omega m, the back EMF follows a similar magnetization curve as that of the BH curve. This curve represents the saturation level in the magnetic system of the DC machine for various values of the excitation MMF or the excitation current IF. Since the back EMF is also a function of the speed, so if the speed changes, the magnetization curve changes also. Therefore, for each speed, we can obtain a different magnetization curve. The magnetizing curve can be obtained experimentally by rotating the DC machine at a given speed and measuring the open circuit armature terminal voltage as the current in the field winding is changed. So we can use a variable DC source to excite the field winding, or we can also use a fixed voltage DC power supply and insert a variable resistance in the field circuit. Both methods can allow us to vary the field current within a certain desirable range. We place an ammeter inside the field circuit in order to measure the field current, and we connect a voltmeter on the terminal of the open armature circuit. Since the armature circuit does not carry any current, the terminal voltage that is measured with the voltmeter is equal to the back EMF. We should drive the machine with a prime mover at the desired speed so that the machine operates as a non-loaded generator. While varying the field current, we take the readings of the ammeter and voltmeter and plot the magnetization curve. So this is how we can obtain the magnetization curve of any DC machine at a given speed experimentally. Now we'll derive the equations which we will need in order to study the performance of DC machines. Since we have different cases or different classes of DC machines, we'll study them one by one, starting with the separately excited DC machine. A separately DC machine can be represented by this equivalent circuit, where RFW is the resistance of the field winding, RFC is the resistance of control rheostat used in the field circuit, then RF is the total field resistance, which is the sum of RFW plus RFC. RA is the resistance of the armature circuit, including the effect of brushes. Sometimes RA is shown as the resistance of armature winding alone. The brush contact voltage drop is considered separately and is usually assumed to be about 2 volts. Recall that in part 3 we have demonstrated the expression of the back EMF and developed the torque as a function of the flux, speed, and armature current. These equations apply to all types of DC machines and do not depend on any classification. Now, if you consider the field winding circuit and apply KVL, we can write that VF is equal RF IF. While the KVL applied to the armature circuit will result in these two equations, one for the motor and the other one for the generator cases. Note that the only difference between these two is the direction of the armature current. So we have in motoring cases, we have minus IARA, and in generator cases, we have plus IARA. For the shunt and self-excited DC machine, the equivalent circuit is as shown here. The standard back EMF and torque equations are the same, and the KVL applied to the field circuit gives this equation, which is very similar to the previous case, but here the field voltage VF is the same as the armature terminal voltage VT. The KCL for motor and generator cases give these two equations. In the motoring case, the terminal current is divided into the field and armature currents, while in the generator case, the armature current is the one that splits into field and terminal currents. Finally, the KVL in the armature circuit lead to these two equations. The only difference in these two equations is the plus and minus signs assigned to the armature current. Similarly, we can find the equations of the series DC machine. Here, the field, armature, and terminal currents are the same current since all windings are connected in series. Therefore, the KVL applied to the circuit leads to these two equations for the motor and generator cases. Note that in the series connection, if the armature current changes, the field current will also change, so they are not independent, in contrast with the separately or shunt connection types. So we can conclude that for the series DC machines, the field flux is affected by the variation of the load. For the compound DC machines, we can proceed in a very similar way. This is the equivalent circuit of the compound short shunt type DC machine, and this is the equivalent circuit of the compound long shunt type DC machine. Notice that both have the same EMF expression, except that the shunt and series fluxes add to each other when the series and shunt windings are connected in cumulative mode, and they subtract when their windings are connected in a differential mode. The equations of the short shunt are shown here, and the equations of the long shunt are shown here. These equations can be easily obtained using the KVL and KCL to the different circuits. For instance, this equation is obtained from KVL applied to this loop. However, this one is obtained using the KCL at this node, while this equation is obtained from the KVL for this loop. The same approach can be applied to find the equations of the long shunt compound type DC machine.